So today's topic is polar coordinate. Okay. How do we convert this thing? Because sometimes this region is not so rectangular, right? But whenever you see a circular region, more the reason to move towards the polar coordinate, right? So let's just think about that. I'm going to sketch a couple of things. Suppose we have this tiny little part of the curve. Well, let's say this little bit of variance here in theta. Actually, I'm going to put that in green. And then I'm going to throw another one like that. So this tiny movement is the theta, right? And then we have a little tiny movement in r direction. Let me zoom in. So this is the theta. And then say this much right there. That is approximately a rectangle now, isn't it? Okay, so this side, we'll call it dr. Tiny little movement in r direction. Oh, this is ugly. Oh, I did not want to do that. I'll just live with it. And this is not d theta, because d theta means on a unit circle, that much is d theta. You know what I'm saying? So how much is this? Arc length. Children, arc length formula. When we say r, this much is r, right? That much is r. Oh no.
R d theta.
R d theta, right? So arc length formula is a biggie. So this is r d theta. So what we have then is your dA in polar coordinate, dA would be r dr d theta, wouldn't it? This times this. You get it? Okay, then now by the way, this r is not just constant r. Let me move that out a little bit. So far it was constant, but this r is a function, and usually this is a function of theta. You know what I'm saying? So this is what you're dealing with. So typically, double integral looks like this. So we'll have some kind of f as a function of r and theta. Good. And then we'll have r dr d theta is our dA. But r is a function of theta, dr d theta, like this. Okay? And then this thingy will move from r1, which is a function of theta, to r2, function of theta, just like y1, y2 as a function of x. And then this thing will change from theta 1 to theta 2. It's typical format of a double integral in polar coordinate. It's like, well, you kind of get it, but you kind of don't at the same time, right? So let's take a concrete example. Okay, we have this volume of a solid that lies underneath this paraboloid and above the xy plane and inside this cylinder, and that's your cylinder. You know what I'm saying? Do you have an image of this volume in your head? Sorry, I asked. This thing. You know what I'm saying? So we have a paraboloid here, and we are going to take circular cookie cutter and cut it, right? We want this thing right there. You get it? This volume is what we want. You got it? Okay, now we'll try to set this up and try to get it. Okay. So first thing we need to do is we have to convert this into polar coordinate, right? So can you feel that this is r is equal to 2 cosine theta a? Y'all feel it? Actually, it tells you right here, so yeah, never mind. I'm sorry. But you could feel it if you wanted to, right? Okay, so that's the first thing. Okay, then now, so we'll set it up. Oh, we need to convert this thing, paraboloid, into the polar coordinate as well then, right? Our function f of x, y, of course, is equal to x squared plus y squared, right? However, if you want to convert it into polar coordinate, and then f of r theta, what would that be? Would that be r squared? Ain't that convenient, huh? So there are a couple of motivations to do it. This is a coordinate transformation or change a variable, if you will. It's kind of like a use of, not exactly, but you know what I'm saying. We have done things in a polar coordinate before. So number one motivation, the region, right? Whenever you see circular stuff, well, then more the reason to go to polar coordinate. And the other thing is integrand. Wow, that's a nice motivation. It's independent of data, that one at least. You know what I'm saying? Say yes. Okay. So we'll set it up now. Our volume will be equal to double integral. We'll just say it abstractly, like you don't have to do this part, but f of r theta and then dA, okay? And then I'm gonna specify exactly what that means, okay? Our thingy is r squared, right? But then our dA also has r d theta, correct? Say yes. You guys look lost. Are you with me, or like give me some kind of facial expression indicator, this, or I mean, I need to know, right? Don't sit there like zombies saying, what? Okay, now, so that's r cubed. I'll deliberately write it like that. And then r will vary from 0 to somewhere, like, you know what I'm saying? That's where the r, where this is the starting point of r and this is the ending point of r. You know what I'm saying? So 0 to r is equal to 2 cosine theta. You get it? And theta will vary. Now we have to be careful. Do we want to put 0 to 2 pi? Do you want this? I'll just write it and let you guys decide whether this is advisable or not. If you remember anything from chapter 10 last year, you should know the answer to this. Okay, fine. How many loops are here? Oh no, you forgot. We could use another plotting quiz of polar coordinate functions. How many loops are here? Come on, people. There are 2. So guess what happens if you do 0 to 2 pi? Bad things happen, right? So we never do such a thing. So when in doubt, because when this thing turns into negative r value, I mean, like, I think they would cancel out instead of giving you double. So never do such a thing. So instead of that, we'll use symmetry. So I will double it and then go only up to pi over 2. You get the idea? You see why we have to do such a thing? Okay, now we can integrate, okay? So this is equal to 2 times from 0 to pi over 2. And this is r cubed, so this is r to the fourth, right? R to the fourth over 4. And then r will start from 0. I'll just write down. I think you guys know what we mean by if I drop r, right? Like that, and the data. Good? Say yes. Okay, now we plug it in. Okay, if we plug it in now, I still have 2 here, and 0 to pi over 2. Now 2 to the fourth power. We'll cancel this, right? So we'll have 4 cosine to the fourth power theta to theta. Do you remember from last year how nasty this thingy was? Yeah, let's figure this thingy out. Okay, on a side. Identity review time. Okay. I'm gonna start here, all of it. I think I need all of this 8, 2 and a 4. 8 cosine fourth power theta. Okay. That is equal to, first of all, this is cosine squared, eh? So I have square, and tell me what cosine squared theta is. Here's a hint. You have a denominator 2. Somebody say it.
1 plus cosine 2 theta.
Oh, good. At least you remember this identity. So do you see that this becomes 4 cancels A, so we have 2, 8? And then we'll square that out. So we have 1 plus 2 cosine to theta plus cosine squared to theta A. Say yes. Oh, come on, people, say something. Okay, and then we do this one more time. So we have 2, and then we have 1 plus 2 cosine to theta. And tell me what that thing is. And you have another denominator 2.
1 plus cosine 4 theta.
Now let's distribute 2 and simplify everything. Okay. So we have 2 here, and you'll pick up 1, so you have 3. Good. Plus 4 cosine to theta. And that thingy, 2 cancels, so we just have plus cosine 4 theta. I mean, that was my motivation to bring that 8 over with me, because otherwise it's a lot of fraction, and eventually we'll cancel that 8. Good? Okay, so we'll come back here. We're back. So this thingy is same thing as integral from 0 to pi over 2. All of 8 has been baked in. So we'll have 3 plus, oh, that's ugly 3. This glove is really slippery. 3 plus 4 cosine to theta plus cosine 4 theta, right? Cosine 4 theta. Like that. So far with me? Okay. Integrate. So we'll have 3 theta, my plus. This will be sine 2 theta. So chain rule, positive, and we'll have 1/2. So we put 2 here, right? And then plus this will be sine 4 theta. Therefore, chain rule, put 1/4 here, and from 0 to pi over 2. Good. Substitute pi over 2, so we have 3 pi over 2. Pi over 2 here becomes sine pi, that's 0. Here, oh, that's 0, and that's 0. So this is it, eh? How about that? Amazing, isn't it? You see how the polar coordinate works out? It's almost the same way, except you just need to vary r from pole origin to wherever that function is. You get it? And then other thing you have to remember is that dA is equal to r dr d theta from up here. Okay? And that r is a function, typically. Okay, let's take another example. And this is a great example. Okay? In statistics, this Gaussian curve. Okay, I'm gonna copy something and make it appear on your space. This Gaussian curve, remember Gaussian distribution? And this is asymptotic behavior from infinity to infinity. We want to find that area. How are you going to do that? Okay. Huh. Do you remember last year that I said someday I'm going to show you how to find that entire area, and then this entire area will turn out to be square root pi? Do you remember that? Okay, maybe not, but today is that someday. Finally, we get to see how to evaluate this integral. Okay, so this integral is given by negative infinity to infinity of e to the negative x squared dx. Now that x is ugly. Dang. And then this thingy integrand, I told you last year, there's no known antiderivative of that function. At least I don't know what that antiderivative is. What? Without even knowing the antiderivative, how can we evaluate that integral? And this is infinity to infinity. Right? That's a daunting task now, isn't it? Yes, it is. Okay, let's get to this. So first thing I'm going to do is I'm going to say square root of the whole thing. See, I'm going to square the thingy inside. Like that. You know what? I'm going to square. I'll just write dx here. Okay, squeeze a little more space out of it. I'm going to square the whole thing like this, and then take a square root. Is that the same thing? It's the absolute value of that thing, but it's the area and it's positive, so it should be the same thing. So far, so good? Say yes. Okay, now I'm gonna play a little trick. So still same square root, but I'm gonna, negative infinity to positive infinity. I'm gonna write it like this, negative infinity to positive infinity, e to the negative x squared dx, and times another integral of negative infinity to positive infinity, e to the negative x squared dx. So far, so good? That's what square means. I just taught algebra 2 rule of exponents, so, right? So far, you're in agreement. Nothing confusing here, right? Okay, this is distance learning, so I get to do this. And I'm gonna paste that thing right here. Okay, so it's exactly the same thing. I mean, exactly identical looking thingy, except now it doesn't matter. We don't have to have a variable x. You know what I'm saying? Because these are known as the dummy variable. Once you integrate it and substitute infinities out, then they disappear, right? So if it's convergent, this is still the same thing now, isn't it? Say yes. Who's confused now? Because it doesn't matter what you integrate with respect to, it's the same shape. Okay. Now I'm going to say that is equal to square root of, I'm going to combine these two integrals into double integral. Because the x's and y's are independent of each other, so it doesn't matter, right? So I multiply it, so e to the negative, and I'm going to write it like this. X squared plus y squared, still the same thing, dx dy. How are we doing so far? Okay, you kind of get it, but you don't at the same time now. This is where you start to lose it. Okay, now do you see the motivation of going to polar? X squared, y squared? Yeah, let's go polar. Okay, I always told you to sketch this region, right? So let's sketch it. There, all of it, right? Infinity to infinity, infinity to infinity. Okay, dang, huh? Okay, let's convert it into polar now. So we still have gigantic square root. And tell me how to convert this into polar. Well, I'll do this much, right? What is dx dy, which is dA in polar? We just did it.
dr d theta.
Not we're missing much.
dr d theta.
Or dr d theta. Wait a minute. Do you see a u sub coming up? Ah, yes, this is u sub. This is a magic trick right there. So all you have to do is figure out the limits of integration. So R varies from what to what? Somebody else tell me, looking at this region. R varies forever. It's not a trick question. It should be obvious. Oh my God. Yeah, 0 to, instead of negative infinity to infinity, 0 to infinity, because this thing starts from the pole. You get it? And theta varies from 0 to 2 pi. I was too afraid to just ask you, so hey, I'll just write it down. That square root is ugly. Good. Now we know how to evaluate this, right? So let's do it. So this is equal to square root of, do you see this is a u sub? Should we just do u sub in our head? Or you wanna change the variable to u and do it? I think we can just do it, right? So from 0 to 2 pi of, that thingy will turn out to be e to the negative r squared, and we just need to adjust it negative 1/2, right? Do you agree? Do you agree with this antiderivative? Okay, now, of course, last year I warned you about, oh, this is improper limit. We have to write limit and be approaching infinity, and then don't be substituting infinities in, right? But that's last year, because you had to take AP exam. Now you don't have these, AP graders anymore, and nobody cares, right? I certainly don't. So let's substitute infinities, shall we? Yeah. So 0 to 2 pi, what do you have? Using plumbing professor, this one first? Or whatever, right? This thing, if you put infinity, e to the negative infinity power is 0, isn't it? So only thing that survives is e to the 0, which is 1 with that 1/2. So we just got this, right? Huh, that's nice. So we'll have square root of 1/2 theta, eh? Theta varying from 0 to 2 pi. We are done. Square root pi, as I promised you. Amazing, isn't it? And this thingy is used a lot in statistics. How many of you are taking AP Stat right now? And then you normalize it by dividing this whole thing by, so usually instead, if my memory serves me correctly, the function, the Gaussian function, is like e to the negative x squared. Is there over 2 here? Or is that just this? I don't remember. If this is the case, then they just put this. Why would they do that? This is known as a normalization, because the area of that whole thing is square root pi. So if you divide by square root pi, then that function has area exactly 1, which is what you want in probability, 100%. You know what I'm saying? Or because my memory does not serve me correctly, or was there a 2 here? Or is there sigma here? Whatever, you can adjust it. This is horizontal stretch. So now area is 2 square root 2 pi. So just adjust it like that. You know what I'm saying? So you see these looking Gaussian function a lot in stat. And even at college level, they say, oh yeah, this is too complicated. So we put it into Z table because they don't know how to integrate this. And remember that Z score or that. None of you takes that, so you don't know what I'm talking about now, do you? Anyway, all of that comes out because they don't know how to integrate this. So they have a table and value of this probably is this function. And then they just figure out the area of all of it. So that's the theory behind this. So this is a great application to statistics.